Okay, so last time we talked about long divisions of polynomials. So if yes,
I think it was someone writing in the chat only, not a raised hand.
okay. Let's see. Okay. So if we have two polynomials, let's say f and g, in coefficients in some field f, so this is like the set of all polynomials, we proved that there exist unique polynomials q and r in fx, such that f is equal to gq plus r, and 2, the degree of r is strictly smaller than the degree of g. Right? And we call this a polynomial quotient. And this guy is the remainder. And I didn't do any examples, so let me show you by example how it's done. Let's see what I have here. So suppose I want to have f as 6x cubed minus 2x squared plus x plus 3. And g is x squared minus x plus 1. So I will use the notation of long division of integers. So I put f here. And here I put x squared minus x plus 1. And so now I'm looking for a monomial to multiply g with, such that after I subtract the monomial times times g, I cancel out the top monomial of f. So this is in fact 6x. If you multiply 6x by x squared minus x plus 1, you get 6x cubed minus x squared. Sorry, minus 6x squared plus 6x. And after I subtract, I cancel out the top monomial. So I get 4x squared minus 5x plus 3. And now I take this remainder. This you can call maybe R1. And I do the same thing. So now what monomial do I need to multiply G such that when I subtract the result from R1, I get rid of the top monomial of R1? Well, this is 4. So I add 4 here. And if I multiply 4 by Gx, I get 4x squared minus 4x plus 1. And I subtract, I get minus x minus x plus 2. I multiplied everything by 4, sorry. So the constant is to be 4. And then I get minus 1 here. Okay, so the result is that, and you can check it, 6x cubed minus 2x squared plus x plus 3 is equal to x squared minus x plus 1 multiplied by the result, the quotient, 6x plus 4, plus the remainder. So I guess you could say minus x plus 1. Okay, is this example clear?
Yep.
All right. So I remind you the slogan. Maybe we put it here. Polynomials are analogous to integers. Okay, so and the one component of this analogy is that you can do long division. But in fact, a lot of the facts about integers follow from long division and prime integers, right? And we have a good analog of prime integers in the realm of polynomials, and this is the following definition. A polynomial f is prime and sometimes prime is replaced by irreducible. If it cannot be decomposed as f equals a times b with degree a and degree b strictly bigger than 0, so bigger or equal to 1. Okay, so a polynomial is prime if I cannot express it as a as a product of two non-constant polynomials. I mean, of course, if I allow constant polynomials, then I can always express a polynomial as in many ways, typically, as a product of two polynomials. One would be a constant, and the other would be just a modified version of the polynomial f. So this is ruled out in this definition. So if you take a linear polynomial, any polynomial of degree f of degree 1 is prime, right? I mean, by degree reasons, if you present it as a product of A and B, then the degree of one of them must be. I mean, if they are not constant, you have a contradiction to the degree. So all polynomials of the form alpha x plus beta are prime. Now, we can take F to be the field of three elements, F3. And I claim that this polynomial fx equals x squared plus 1 is prime. If it wasn't, then it would be a product of two linear polynomials. And since f has 1 as its coefficient of the leading monomial, I would have x minus a, x minus b for some a and b in f. But you can check that f does not have any root. I mean, 1 squared plus 1 is 2, which is non-zero, and 2 squared is 4, plus 1 is 5, which is again non-zero. Now, if you take the same polynomial over a larger field, if you take f to be f5, and f the same polynomial as before, then f is not prime. For example, I can find a root. I mean, in fact, you can so 3 squared plus 1 is going to be 10, which is 0 modulo 5. And 2 squared plus 1 is 5, which is 0 modulo 5. So f, or x squared plus 1 is x minus 2, x minus 3 is not prime. Okay, so of course the expected property about prime polynomials is that you can decompose every polynomial into a product of prime polynomials. This is true, but we also want uniqueness, and for uniqueness we have a problem with the possible coefficient of the leading monomial. So what we do is we restrict attention to monic polynomials, i.e., where the coefficient of the leading monomial is 1. And then we have this proposition that f be a monic polynomial, then there is some k, and monic polynomials, monic prime polynomials, a1 up to ak, such that f is equal to a1 up to ak, and a1 up to ak are unique up to reordering. Is this statement clear, especially the last part of uniqueness? Okay. So how do we prove it? Yes.
Just to make it extra clear, the f, you multiply all the primes polys a1 to ak. It's not like composition, it's just multiplication.
No, multiplication. Yeah, multiplication. I'm trying to ease the notation with not writing the variable. I think it stresses the analogy to integers better.
Yep.
But okay. So how do we prove this? Well, existence is basically the same argument as you do in integers. I mean, if f is not, if f is not prime, then it is a product of two primes. It is a product of two polynomials. which are of smaller degree of f. And if they are not prime, then each of them is a product of two lower degrees. And since you reduce the degree every time, this process has to stop. So, and when it stops, you are left with a decomposition of f into a product of prime polynomials. So existence is clear. For uniqueness, yes.
Yeah, sorry again. So when you say if f is not prime, it must be the product of two polynomials. But in this case, there could be a reminder. There could be error x, which is not new.
No. If you look at the definition of prime, prime means that it cannot be decomposed as a product, as a non-trivial product, let's say. Okay. So not prime means it can be decomposed as a non-trivial product.
Okay.
Right? If you wish, if it helps, I can write it down in detail for the existence. I mean.
No, it makes sense now.
Okay, it's really just like in integers. If you have an integer, if it's prime, you're done. I mean, you want to prove that an integer is a product of primes. If it's prime, you're done. If it's not prime, it's a product of two integers. Both of them are smaller than this original integer. If so, one of them is prime, you look at the other and you keep repeating this. So eventually you have to stop, and this gives you a factorization.
Makes sense. Thanks.
Yeah. Now for uniqueness, suppose I can write f in two different ways. A1 up to AK, and B1 up to BL. Remember, I mean, if I do not know uniqueness, then possibly f could be a product of prime polynomials of different length, right? I mean, a different number of prime polynomials. So this is the K and L here. Where AI, BI are monic primes. Now I claim A1 it cannot appear on the left hand side. Okay, so I suppose, sorry, let me amend the argument. I suppose that I have a polynomial with two different factorizations. That f is of minimal degree such that you have two different factorizations. Okay, so if it is of minimal degree, then A1 cannot appear on the left-hand side, because then I could cancel it out and I would get a polynomial with with lower degree than f that still has two different representations of product of prime polynomials. So A1 cannot appear on the left-hand side, since otherwise we could cancel it and contradict the minimality of f. Similarly, B1 cannot appear on the right-hand side. Okay, so without loss of generality, let's suppose that the degree of B1 is smaller or equal than the degree of A1. Well, okay, then I can do long division of A or A1 by B1. So there exists a Q and R such that A1 is equal to B1 times Q plus R, with the degree of R strictly smaller than the degree of B1. Okay, now since the degree of R, well, R has a prime factorization. So R has a prime factorization. Let's say R is equal to some constant, alpha, times R1 up to Rm. And here I have to add some constant alpha, because I cannot assume that R is monic. And in fact, alpha is non-zero, right? Otherwise, this whole becomes trivial. And moreover, B1 does not divide any of the Ri, since B1 has higher degree because of degree reasons. Well, okay, now I substitute this this identity and this identity. So I get let's say a Q B1 plus alpha R1 up to Rm. This is basically A1, right? So now I multiply by the rest of the A's. So it was A2 up to AK. And this has to be equal to B1 up to BL. Now, let's set F prime to be this product R1 up to Rm times A2 up to AK. And I can write F prime as, if you check it, it's going to be the inverse of alpha times B1 up to, well, B1 times B2 up to BL minus Q A2 up to AK. Okay, this I obtain, I mean, from star. Right? So I just renamed something as F, right? I have here this guy in pink is F, and then I just I move things to the other side, take a common factor, I get this double star. But of course, R1 up to Rm, A2 up to AK is another, so I get, so we get two factorizations of F prime, right? I mean, of course, you can further factorize this component, but in whatever you have, where B1 appears in one factorization, but not in the other. And the degree of F prime is strictly smaller than the degree of F, because remember, F prime is this product, and I removed some. I mean, it is of a lower degree than F. So this is a contradiction to the minimality. To minimality of degree F. Okay. Any questions about the proof? Now is the time. Is it? Are you comfortable with the proof, or I can explain again in a sketch what is going on?
Yeah, for me, maybe it would be useful.
Okay. So, what is? I mean, I want to prove that if I have a monic polynomial, I have a unique factorization up to reordering of this polynomial as a product of primes. Now, suppose, so I assume by contradiction or towards contradiction that this is not the case. If it is not the case, it means there exists at least one polynomial, let's call it f, with two different factorizations. But of course, if there exists such, I can look for the polynomial, or let's say a polynomial with two different factorizations that is of minimal degree, right? I mean,
Yeah.
Okay. So I assume that f is such, but with a minimal degree. Of course, it does not mean that f is the only one, because possibly there could be two different polynomials, f1 and f2, that have different factorizations, and both of them are of equal degree, right? But all I need is one. So I assume f is such. Now, because of the minimality of f, a1 that appears here cannot appear anywhere here, because if it would, then I could cancel it out on both sides, and I would get two different factorizations of a polynomial of a lower degree than f, right? So this would contradict.
I see. Yeah. I see.
Okay.
I see.
So, and for the same reason, B1 cannot appear. B1 cannot appear on this side. Okay, because again, I could cancel it out and contradict the minimality of f. So now I do. So I assume that just for convenience, that the degree of B1 is smaller or equal than the degree of A1, and then I do long division. I do A1 modulo B1. I get some quotient and remainder, and the remainder is guaranteed to be of a lower degree than B1. Now I take the remainder and I decompose it into a product of primes. Here, because I cannot assume the remainder to be monic, then I write it as some constant times a product of monic prime polynomials. Let's call it monic prime factorization, but you have this coefficient alpha that you have to add. And I note that because of degree reasons, I mean, because of this, B1 cannot divide any of the Ri. I mean, B1
Okay.
is of degree bigger than R, so clearly it cannot divide any of the Ri.
Makes sense. Makes sense. Makes sense.
Okay, so
Sorry.
now I just do.
Sorry, can you go again? Why you can write R such as this?
So I can. I mean, we said that the existence you can always. So if R is not monic, then let's say alpha minus 1 times R is monic for some alpha. I mean, namely the alpha appearing in the coefficient of the top monomial of R, right? And if R is, just think of like if R is ax to the n plus something,
yeah,
then of course you can write a minus 1 of R. This will be a monic polynomial.
yeah.
And we said that monic polynomials have factorization into a product of monic prime polynomials. Okay. This is the existence part, right?
Right.
Okay, so I can write R in this way. And now I just plug it into the equations, right? Because I have A1 up to AK equals B1 up to BL. But instead of A1, I plug in this, right? And now I define F prime to be basically the product of these purples, right? R1 up to Rn times A1 up to AK. And I claim that this equation star, in fact, gives me two different factorizations of F prime. Well, how do I see it? I can write F prime as this constant alpha minus 1 times B1 times whatever is left. And I can also write F prime as it was originally defined as a product of R1 up to Rm, A2 up to AK. Now, this blue part is a product of prime polynomials. Prime, in fact, prime and monic polynomials that is equal to F prime. What you have here, let's say the purple part, you could also, I mean, you could also express the purple part as a product of prime polynomials. I mean, you take whatever is in the brackets and you factorize it into a product of prime polynomials. What you will get is some constant alpha minus 1 times B1 times some product of possibly non-monic polynomials. But what you get here is that on the purple side, you have B1, and on the blue side, you cannot have B1, right? I mean, because B1 cannot be one of the A2 up to AK because of the original argument, and B1 also cannot be one of the R1 up to Rm because it is of higher degree. So what you get is that you get two factorizations of F prime in which in one factorization you have B1 and in the other factorization you don't have B1. So this is two different, so you can I mean, you can extract from the equation double star two different factorizations of f prime into a product of prime polynomials. But f prime is of degree strictly smaller than f. So this is a contradiction to the minimality. Is this clear now?
It is for me, at least. Yeah.
Okay. So once we have this this kind of anchor, definition. Let f and g be two polynomials. A greatest common divisor and GCD FG is a polynomial that divides both f and g, and is of maximal degree. Okay, now, well, using this this previous proposition, so if f and g are monic, GCD of f and g is unique, because you can decompose f and g into a product of monic prime polynomials and see what is the what are the prime polynomials in each of the decompositions that are common. I mean, it's like you do again. It's like think of f and g as two integers. You write it as some product of primes, p1 up to pk, and I mean q1 up to ql. And you look for, I mean, the GCD is just you take the common primes that appear in the factorization. So you basically do the same thing for f and g. And since for monic polynomials the factorization is unique, then the GCD is unique. For non-monic polynomials, if f or g are not monic, a GCD of f and g is unique up to multiplication by invertible element alpha in f. So a non-zero element. Okay, because of course, if f, let's say f is not monic and g is monic, just take some constant out of f to make it monic. So it will be a product of a constant and monic polynomial, and you will do the GCD to G and to this modified F, and this will be your GCD. It will be unique up to a constant. Is this clear? It's like this subtle point of uniqueness here. Anyone?
Yeah, we put thumbs up. Maybe you don't see it, but yeah, it's clear.
Okay, okay. Now we're going to actually employ the analogy between polynomials and integers in order to get an analog of the Bézout lemma. So let me remind you, I mean, we actually didn't do a proof of the Bézout lemma. But the statement we did, I mean, the statement is for positive integers, let's say A and B, there exist some integers U and V such that AU plus BV is equal to the GCD of U and V. Now, there are many ways to see why this is true. Of course, you could describe an algorithm and show that it stops and so on. This I leave to you to read it other places. Actually, I think there's even something in the notes. But the proof that this is true can be done without any algorithm. So consider the set K to be the set of all expressions of the form AU plus BV, where U and V are integers. Okay, this of course is a non-empty set because you can pick U and V to be 1, for example. And let K, lowercase k, be the smallest positive element in K. Now, since lowercase k is in this capital K set, there exist U and V in Z such that K is equal to AU plus BV. We can also do long division of A by K, and we can write A as K times Q plus R with are strictly smaller than K and bigger or equal to 0. And if I can write this, I can plug it in. So I get R is equal to A minus QK, which is A minus Q AU plus BV, which is A1 minus UU plus B minus QV. So I get that R is also an element in K. But R is strictly smaller than K, and K is the minimal positive element that is in this set capital K. So I get that R is equal to 0. That's the only non-contradictory way. Yeah.
Why cannot R be negative?
Because R is a remainder, so it is a...
Right. Yes, sure. Right, sorry. Yeah, makes sense.
Yeah. Thus, A is equal to Q times K. So Q divides A. K divides A. Similarly, K divides also B. So K is smaller or equal than the GCD of A and B, right? I mean, so K is a common divisor of A and B, so it has to be smaller or equal than the greatest common divisor. Now since the GCD of A and B must divide A and must divide B, and K is equal to some AU plus BV, I get that a GCD of A and B must divide K, right? Because it divides A and it divides B. So the GCD of A and B is smaller or equal to K, and I had the other inequality here, i.e. K is equal to the GCD of A and B. Okay, so I get that the GCD of A and B is some AU plus BV, as I wanted. Any question about the proof? This is the Bezout lemma. And I remind you that the coefficients U and V are typically not unique. But we only care about existence in this case. So try to go over this in the break. Let's take a 10 minutes break. And what I'm going to do after the break is to adjust the argument of this lemma, or the proof of this lemma, to get the same fact for polynomials. Okay? So
Sure.
see you in 10 minutes.
See you.
Okay, can we start again? All right, so the polynomial version of this last lemma is the following. I mean, let F be a field, and A and B two polynomials. Then there exist polynomials U and V such that AU plus BV is equal to the GCD of A and B. If you want, we can make A and B monic, but it's not necessary. So consider K to be the set of all expressions AU plus BV such that U and V are polynomials. In this set, I have elements of a smallest degree. I mean, possibly I have more than one element. I mean, possibly we can have several elements of smaller degree, but I have at least one. So let K in K be an element of smallest degree. So K is equal to some AU times BV. Now I do long division of A by K. A is equal to K times Q plus R, with, of course, degree of R is strictly smaller than the degree of K. And, of course, bigger or equal to 0. So I can write R as A minus QK, which in turn is A minus AU plus BVQ. And again, I can write it as A 1 minus QU plus B minus QB. And so I get again that R is in this set K, capital K. But R is of degree strictly smaller than K, and K is supposed to be the element of smallest positive degree, I should say. So it follows that the degree of R is 0 well, in fact, I want to show that R is really the zero polynomial. So let me take K to be the element of smallest positive degree, or smallest degree, not equal to the zero polynomial. So if I choose K like this, then I get as an immediate corollary that R must be the zero polynomial, because it is a polynomial that can be expressed as A times something plus B times something, and its degree is indeed strictly smaller than K. Okay, so A is equal to K times Q. And as before, so what I get is that A divides K, and similarly, B divides K. So the GCD of A and B has to divide K. Well, actually, what I want is so K is a common divisor of A and B. So the degree of K has to be smaller or equal than the degree of the GCD of A and B, right? Because it divides, I mean, A and B. Oh, I'm sorry. Here it should be reversed. So I get that K divides A and K divides B. So K is a common divisor of A and B. Hence, its degree must be smaller or equal than the degree of the GCD. But a GCD of A and B divides, of course, divides A and divides B. So GCD of A and B has to divide AU plus BV, which is K. And in particular, the degree of GCD AB has to be equal to the degree of K. Well, I mean, it has to be smaller or equal. But this, of course, means that the two degrees are equal. And so, yes, so they are, I mean, in fact, so if we assume AB harmonic, then by uniqueness of the GCD, we get that K is equal to, well, on one hand, AU plus BV, and on the other hand, to the GCD of A and B. And otherwise, well, this will be true up to a constant. So, so you know what? Let's just assume that A and B are harmonic. I apologize for all the patches, but is this proof clear? It's really like a demonstration of the power of this analogy.
For me, most of it is clear. Only the last step where you enforce that A and B are harmonic, and first you can say the last step here.
Okay, so so this is why I modified the statement. Let's suppose that A and B are harmonic. Okay. If A and B are harmonic, then in the last part of the argument, I get, I mean, K is a polynomial that divides A and divides B, and is of the same degree as the GCD. So by the GCD of A and B is unique if A and B are harmonic, and it is the minimal, it is the common divisor of A and B with minimal degree. So if K is equal to the degree of, if the degree of K is equal to the degree of the GCD, they must be equal, right? By
okay, yes.
Uniqueness
So
of
the harmonic to say that the GCD is unique. You need this.
Yes.
Okay,
Yes.
thanks.
So maybe here, since we assume. But what I want you to take from this is really the power of the analogy. I mean, the analogy does not work completely, right? I mean, you could say polynomials are a different object than integers, and factorization into prime factors is not unique unless you talk about monic polynomials. So the analogy is not perfect, but nevertheless, it's very helpful, and you can really like plug it into an argument and see that you get the same. I mean, the same argument is applicable for the polynomial case.
Yeah, it's so interesting that the argument is very, very similar. Just
Yeah, and I don't want to spoil the surprise, but the analogy will help us further into constructing finite fields. So, do I have an example here? I guess not. So, the next thing is modulo arithmetic. Modulo arithmetic of polynomials. So let phi be a polynomial in coefficients in f, be of degree n. Now, if you take a polynomial over f and you do modulo, you do long division with phi, the remainders, the possible remainders you get are basically all the polynomials with degree less than degree of phi. So I can look at the set, I call it f sub phi is the set, so we define, I'll need more space. So f sub phi is the set of all r x equal to, let's put it like this, an minus 1 x to the n minus 1 plus a1x plus a0, where the ai's are elements in f. Okay. This is the set of all possible remainders of long division let's say f long division phi, or for general polynomial f. Right? Clearly the remainder has to be of degree smaller than the degree of phi. And any polynomial of degree n minus 1 or lower can be obtained as long division. For example, take this polynomial r and do long division with phi, then by definition the remainder is r itself, because you start from something with a degree strictly smaller than the degree of phi. The long division terminates at the beginning. So f phi x is the set of all possible remainders. Now on f phi x we have, I call it mod phi arithmetic. Namely, you take let's say you take r and s in f phi x. You can do r plus s modulo phi. Right? In fact, this would be, by definition, it will simply be r plus s as polynomials. And you can also do r times s. You do r times s, and then mod phi is simply defined to be r times s, the remainder of r times s in long division by phi. And these operations are going to be associative. So let's see Why? I mean, well, actually, not sure it's worth. Let me put it in brackets. You can check it yourself, but it's really associativity of addition and multiplication of polynomials give you associativity of these modulo operations. I mean, for example, if you do so, let's say so if you have R equal to F modulo phi, and you have S equal to G modulo phi, then you can write R as, F as quotient times phi plus R. And you can write G as, let's say, T times phi plus S. But then F plus G is going to be equal to Q plus T phi plus R plus S. So you see that that F plus G modulo phi is equal to R plus S. Right? So in fact, I could have defined this this set F phi E, I mean F phi X as a set of all polynomials. It's like I do, and again, this analogy, I mean, how do you define integers modulo n? You can look, one way is to look at all the integers and well, you define kind of equivalence classes. You say, if I take any two integers, the addition and multiplication, I just do a regular addition and multiplication, and I do long division by n and take the remainder. And another way to define the integers modulo n is to say, okay, I look at all possible remainders, 0 up to n minus 1, and I have addition and multiplication modulo n on this set. And again, this is given by the long division. So what I get in this polynomial case is really completely analogous. I can do addition, multiplication, modulo phi, and so okay. You can see similarly that if you take F times G, in this case, right? F times G is going to be equal to R times S modulo phi. And so what we have here well, we have almost a field, right? We have addition, we have multiplication. Maybe before this theorem, of course. So phi x is almost a field, and I mean, if you want the additive inverse of R is simply minus R. Zero is neutral to addition. And one, I mean, the polynomial, the constant polynomial, one is neutral to multiplication. But we don't have an inverse for an element in this funny set f sub phi. If phi is prime, f phi x. In fact, I guess we can say it's an only if and only if phi x is prime, is a field, if and only if phi is prime. Before I go to the proof, any questions about this modulo phi arithmetic? Right. So, but the proof is really, really easy. We did all the preparations, so it's gonna be quick. If phi is not prime, write phi equals to f times g with degree f and degree g bigger or equal to 1, and of course strictly smaller than the degree of phi. Then since f and g are of a smaller degree than phi, I can really look at them or view them as elements in this f sub phi. And I get that if I do modulo phi arithmetic, f times g is equal to 0 modulo phi. So I get two non-zero elements whose multiplication is 0, and this cannot happen in a field. You remember we had a lemma, like an observation, really, that in a field, if you multiply two elements that are non-zero, you cannot get 0. So f phi x has 0 divisors. And it cannot be. Okay. Now, conversely, suppose phi is prime. And let R be some arbitrary element in this set of remainders. Then the GCD of R and phi is 1, right? Because phi is prime. Phi is prime, and R is of degree smaller than phi. So the GCD has to be 1. Hence, there exist polynomials A and B in f of x, such that polynomials U and V, if I'm consistent in the, such that RU plus phi V is equal to 1, i.e. RU is equal to 1 modulo phi. So U is a multiplicative inverse to R. Okay? Hence, f phi x is a field. Here I should say R not equal to 0. Of course, say monic, I could do it first for monic polynomials R, but if a monic polynomial has a multiplicative inverse, then all the non-monic polynomials have a multiplicative inverse, because I can always express a polynomial as a constant times a monic polynomial. Corollary. If f is equal to fp and phi a prime polynomial, then f sub phi is a field with p to the n elements where the degree of where n is equal to the degree of phi. Okay, this corollary does not require a proof. I mean, you just count what are the possibilities of all remainder polynomials. I mean, over fp, you basically have to choose the coefficients a0 up to an minus 1. And they could be anything. So you get p to the n options for all the remainder polynomials. Any questions about this theorem? It's basically existence. Well, it's more or less existence of fields of P to the n elements. I get the feeling that it was not completely clear, but I need to hear what is missing. Carlos, what do you think?
It was clear for me.
Okay, so it's clear, but again, what I want you to take from this is really, if you think of it, this proof is almost exactly the same as the proof that modulo, I mean integers modulo a prime are a field. I mean, you use the Bezout coefficients to find the multiplicative inverse. The multiplicative inverse is the only non-trivial axiom that you need to check in order to verify that integers modulo a prime are a field, or in this case, polynomials modulo a prime polynomial. So let's do an example. Maybe this would help a bit. So let us construct a field with 4 elements. So I take a polynomial of degree 2 over f2. So let f be f2, and phi is the polynomial x squared plus x plus 1. And then phi has, has no roots over f2. Hence, phi is prime. I mean, how do you see it has no roots? In this case, you simply you can do a brute force. I mean, you substitute 0 instead of x, you get something non-zero, you get 1. And you substitute 1, you get 1 plus 1 plus 1, which is still not 0. So I took a prime polynomial over f2. Now the set of all possible remainders, f x, is basically it's all polynomials of degree 1 or less. So it is x squared, sorry, x plus 1, 1 and 0. Right? This is the possible remainders. Let me reorder it. We'll say 0, 1, x, and x plus 1. Now I can tell you the addition and multiplication tables. So I do 0, 1, x, x plus 1, 0, 1, x plus 1. And if you do the calculation, I mean, of course, I get here 0, 1. Sorry. 0, 1, x and x plus 1. But when I do, well, 1 plus 0 is 1, 1 plus 1 is 0. 1 plus x is x plus 1. So you see the addition is really trivial. I can complete it for convenience, but this is x, and I have x plus 1, 0, 1, and x plus 1, x, 1, and 0. So this is the addition. The multiplication is slightly less trivial, but it's very, very simple. Here, well, at the 0, I get 0. And now I will get 1 x plus 1, 1 x plus 1. And the only non-trivial thing is to notice that x squared is equal to x plus 1 modulo phi. So here it's x plus 1. And here I'm going to get 1. And here x plus 1, x is 1. And x plus 1 is going to be x. So, right, I mean, you can see just to justify some of the, I mean, let's say, to justify this purple cell, I mean, x squared is going to be equal to minus x plus 1 modulo phi, but I mean phi is x squared plus x plus 1, right? So this is the same thing as saying like x squared plus x plus 1 is equal to 0 modulo phi. I simply moved something to the other side, but minus x minus 1 over f2 is simply x plus 1. Okay, so this is the addition and multiplication table, and we get a field of 4 elements. You can check that it's actually isomorphic to the field of 4 elements that we kind of defined in the I mean a couple of sessions ago with the elements 0 up to 0, 1, 2, 3. So it's another presentation, but it's a concrete presentation, right? However, the problem, well, at least one problem is that we don't know that prime polynomials exist in every degree over any field. At least from what we saw, it doesn't follow. So the existence of a field of p to the n elements for any n is not yet guaranteed. However, there are polynomials, are prime polynomials of arbitrarily large degree. Let's say over FP. Otherwise, if the prime polynomials can only exist up to a certain degree, there would be finitely many prime polynomials over FP. Say we can call them A1 up to AK, but then you take A1 and you multiply it up to AK, and you add 1, is also prime. Right? Because for each I, AI does not divide, let's call it A, does not divide A, right? It has a remainder 1 if you do long division of A by this AI. And we said that A1 up to AK are all the prime polynomials. So yeah. Yes? Okay. So what you get from this argument, which is again, so this is a contradiction. It means that I have to have infinitely many prime polynomials, and so of course I would get fields f sub phi, or fields of p to the n elements with n as large as I wish, but possibly I don't know that for every integer n I can get a field of p to the n elements. Okay, I guess this is time to wrap up. So any questions about what we did, or requests for next time?
Thank you.
All right. So see you next week.
Bye. Thanks.
Bye bye. Thank you.
Thank you.
Thank you.
Bye bye.
See you.
See you.